Thank you very much for the introduction, and thanks to all of you for coming, even though I heard that there were other talks around. I'll do my best. Thanks for inviting me. So I'll speak about some joint work with Lea Beneish, Henri Darmon, and Lennart Gehrmann on the Gross-Kohnen-Zagier theorem for the case of Shimura curves using p-adic uniformization. And what I'm going to do is I'm going to begin explaining an example of a theta series, because the Gross-Kohnen-Zagier theorem can be seen as a geometric generalization of what theta series are. So we are going to start with this first instance, and we'll motivate this example with what some people call the Fermat business theorem. And this theorem is about which prime numbers can be written as a sum of two squares. So probably you have seen it. So it says that a prime P is the sum of two squares. Even on D, P is equal to 2, or P is equivalent to 1 or 4. So, as you can imagine, even though this theorem has the name by Fermat, Fermat didn't prove the theorem, as it happens with theorems of Fermat, with some. The first person who proved it was Euler, but today we're more interested in an approach due to Jacobian. And what Jacobi studied was not only which numbers can be written as sum of squares, but in how many ways you can write a number as sum of squares. So he studied these quantities that I'll call Rn, which are the number of ways that you can write n as a sum of two squares. Namely, the number of pairs xy in z squared such that x squared plus y squared is equal to n. And the way that he studied these quantities was by packaging them into a generating series. So we can consider the generating series theta of q made out of these numbers, Rn times q to the n. And observe that we can reorganize it by saying that we take a sum over vectors in a lattice z squared of q raised to the length of a vector. This is just a reorganization. And this will be an example of theta series, by the way. And now, what happens when you want to study these quantities Rn and you put them into a generating series? One technique to do this is to now try to study properties of the generating series and hope to, out of these properties, maybe you find the recurrence or something like this, you get information about the numbers inside. And here, maybe what is remarkable is that instead of studying properties of this just as a formal power series, is that if you do the change of variables q equals to e to the 2 pi I tau for tau an element in the upper half plane. So these are the complex numbers. The complex numbers with positive imaginary part. Then q will have absolute value smaller than 1, so this sum will converge. And this defines a holomorphic function. And the nice thing is that this function satisfies a lot of very nice symmetries. So now if we do theta as a function on tau, so theta of tau is a holomorphic function, and so has some nice symmetries. So the first one is simple, which is that it is a periodic function. And this is easy because it's a function on the exponential. And the next one is more interesting, and it goes like this. It says that theta of minus 1 over 4 tau is equal to 2 tau divided by I times theta of tau. This is a bit more involved, But the way it's proven is using Poisson summation formula and using the fact that the exponential is essentially its own Fourier transform, or the Gaussian vector set. And this gives a non-trivial relation that you can summarize like this. And the functions that satisfy these equations are actually an instance of a modular form. So this can serve us to motivate what is a modular form. So a modular form of weight k, k is an integer or half of an integer of weight k and level gamma as subgroups of S to Z. Is a holomorphic function from the upper half plane to the complex numbers that satisfies certain growth conditions, but that I will not enter into writing it, but that it satisfies a symmetry of this sort, which is that f of a tau plus b divided by c tau plus d is equal to c tau plus d to the k times f of tau. And this has to happen for every matrix A, B, C, D in this level gamma. And so then the way we would summarize these symmetries using the language of modular forms is that saying that theta is a modular form of weight 1 and level is written like this, gamma 1 of 4. And these are the matrices A, B, C, D, congruent to 1, 0, 1, and here whatever, mod 4. So here basically what happened is that, so to study this problem about sums of squares, we make a generating series out of the numbers we want to study. And we saw that they satisfy very nice symmetries. And now I just explained that this is actually one of the things that motivates the theory of modular forms, and write the definition in more generality, because we'll need it later. But now the point is that kind of the study of modular forms can be done using complex analysis, for instance, or representations of groups like SL2. And thanks to the study of modular forms, you can end up deducing something about the theta function, the original one. And this is what will happen. So for instance, using the theory of representation theory of SL2, one can find other functions that transform in this way. In a way, this is essentially like being invariant, so you can kind of do some sorts of averaging. And this leads to another example of a modular form. Of a modular form of weight 1 and level gamma 1 and 4, gamma 1 and 4, that I'll write like this. M being the modular forms of weight 1 and level gamma 1 and 4. Another example is what it's called the Eisenstein series. And this one, it's written, it has the following Fourier expansion or Q expansion. It's 1 plus 4, sum over n. And now the Fourier coefficient, the coefficient of q to the n, it's a divisor function. You sum over the divisors of n of this function, chi4 of beta tau is the moment, times q to the n. Where chi4 is a character that gives an isomorphism between z mod 4 z star and plus and minus 1. So this is another example that can be found of modular form. And you can see that it also in a way encodes interesting number theory data because it's sums of divisor functions. So it's in a way also interesting. And the nice thing is that using complex analysis, one can show that this case of modular forms is one-dimensional. And so therefore, this function that we wrote and the theta function have to be proportional. So, but in fact, M1 of gamma 1 of 4 is one-dimensional as a C-vector space, and therefore theta of tau has to be a multiple of E. But if you look at the constant terms, you'll see that they are actually equal because they both have constant term 1. And in this way, we just deduce a formula for the number of ways of writing n as a sum of two squares in terms of divisor functions. So if now, so we could prove even more than Fermat, but if we care about Fermat, what this is telling us that the way of writing p as a sum of two squares is 4 times 1 plus chi4 of p. And now you could see, write it down and see, okay, if p is 2, chi of 4 here is considered to be like 0, because it's an element that it is not coprime to 4. So if p is 2, this just gives us 4. And you can see that there's only 4 ways of writing 2 as a sum of two squares. We're putting signs, plus or minus 1s. So here is up to sign. If p is congruent to 1 mod 4, then we will get 8. And otherwise we get 0. So that's the idea. And so what we aim to do today is to see some geometric analog of this theta series. Some geometric analog of theta. So this will mean that we replace the numbers Rn's by points on curves, on certain curves, and then the fact that this is a modular form will also have some nice arithmetic consequences, in the same way that the fact that theta was a modular form would tell us some arithmetic consequences. And arithmetic consequences. I will not enter a lot into it, but I'm happy to, if you're curious about something, to say more. Okay, so that's the goal. Yes, please.
Could I please ask about how do you prove that the space is one-dimensional? So is it something like Riemann-Roch theorem or?
Yeah, so I think maybe it's something on these lines. But for instance, like the proof I have in mind would be that you try to study how many zeros a modular form can have. If you have a modular form of weight 1 and level gamma 1 of 4, you try to study how many zeros it could have using a bit the residue theorem.
So it's not very difficult.
Yeah, no. It's quite. You need to know complex analysis and understand a bit this loop gamma 1 of 4. But you kind of bound the number of zeros, and then if two modular forms were equal, or like you could see how many zeros the difference between these two things could have, and if it has too many zeros, then you consider the proportion. Yeah, of course. Thanks for the question. Okay, so now the thing to do that I will do, since we want to do a geometric analog of theta, I will introduce the geometric ingredients that will play a role. And in this case, this will be Shimura curves that will study via something that is called p-adic uniformization of Shimura curves. And certain points in there that are called special points or Kibner points. But let me say that I'll focus on this geometric generalization, but there's many ways to generalize this theorem. So I'll stay kind of in a particular case that can be studied using this p-adic theory. Okay. So maybe for the people that have seen modular curves here or Shimura curves, we usually study its complex points, and we study them as quotients of the upper half plane by some group of arithmetic interest. And now what I'm going to do is a p-adic version of this. But I'll try to explain it without relying on the classical story. So we'll consider this space that is called the p-adic upper half plane, HP, that it's defined as a set as P1 CP minus P1 QP. And maybe this looks a bit scary, but you can see that this is a bit similar to the usual upper half plane, that it is P1C minus P1R. But maybe you take a connected component in that case. You take the upper half plane, it will be C minus R, the upper part. This is a p-adic version of this. And this has a nice theory of analytic functions, and it's called the residuality space, to have, if you have such a nice theory. And what now we do is we try to find arithmetic groups that act on this space, and hoping to understand these arithmetic groups by understanding these actions and the quotients that you get. So for this, I need to take V, a definite quaternion algebra. By the way, here P stays to be a prime. Definite quaternion algebra over Q.
What's the OP here?
Sorry, this should be a QP.
Oh.
Sorry for that. QP.
Thank you.
Yeah. So it's the completion of the rational numbers with the p-adic metric. So we take V, a definite quaternion algebra over Q of discriminant B with D prime P. And the type of groups that will act on HP will be some groups of units of orders in B. So for this, let me take R as Z1 over P, Eichler order. If you don't like Eichler orders, you can just think it's any order or a maximal order in D. And gamma the groups of units of this order that have normal magnitude. So here it doesn't exactly apply, but the easiest example to think of mine is that the quaternion algebra is the algebra of matrices M to Q. It's true that it's not definite, but just for a moment, M to Q. Then the order you would take is M to Z, the matrices with integer coefficients. And then the units would be SL to Z. And this would be a bit similar to the type of things that we were studying modular from. Sorry for the
By definite, you mean that it stays non-trivial over the real numbers?
Yes. Yeah. So yeah. So the example I said is not exactly. The point here is that since we wanted to act on this space, the p-adic upper half plane, what is important is that the quaternion algebra will be split at P instead of being of carrying what happens.
That was my other question. What's the discriminant of a quaternion algebra? I don't know what that is.
Okay. So one way to think of the discriminant is to think that the quaternion algebra over Q, we can see, we can tensor it with any prime QL, and this will either be an algebra of matrices M to QL, or either be a division algebra, and the discriminant is the product of all the places where this thing is a division algebra.
Also at 2?
Sorry?
Also at 2?
I think yes. I mean, honestly, I haven't looked at the definition in a long time, so maybe if someone wants to object. But that's a bit the idea.
Plus minus 1 depending on...
Yeah, and then plus minus 1 depending on the behavior at infinity. If at infinity is M to R, or if it is the Hamilton quaternions.
But if we say that it is non-trivial at over R, does it not say that the number of QPs where this non-trivial is odd?
Yeah, there's some conditions of this sort. Indeed.
So it would be minus 1 or the discriminant then? Or...
No, I mean, there's, for instance, the Hamilton quaternions. I think they have discriminant maybe 2 or minus 2 or something like this. And you have that at 2 it also stays a division algebra, and at infinity it's also a division algebra, and at the other places will split. But you're right in saying that not every discriminant is allowed. You cannot choose any D and construct a quaternion algebra. There's some conditions about the number of primes where the quaternion algebra becomes a division algebra. You
So
can
it's a number which counts the number of
the number.
cases where something happens, and with a sign which also has a meaning.
Yes. At least I think this for practical reasons is how I think of it. Yeah. Yeah. Thanks. So maybe I'll take the chance since we discussed this to say that for us the key thing is that B tensor QP stays M2QP. Because I took that the discriminant is prime QP. This is what will be very important for us. And I mean, of course, also, even though we will not use it explicitly, it's also important that it's definite. So,
Sorry, can you say again what this R is? Is this some?
yeah, R is an Z1 over P order in the quaternion algebra.
Just any order?
Yeah, I mean, here I set an isolar order. An isolar order, it means that it's the intersection of two maximal order.
Okay.
Here, this is a bit more behaved, a bit better behaved because it would be the type of things that for matrices it would give. The units would be the matrices that are congruent to that the lower range is congruent to 0 mod n or something like that. But for the purpose of this talk, it's not very relevant. Yeah, thanks. Perfect. So the key thing about B tensor QP being M2QP is that now we can make B star act on the p-adic over half plane by modulus transformations. Because, and in particular, we can make gamma. So we can take gamma, put it inside B tensor QP star, and this will be something like GL2 QP, and therefore act on HP by modulus transformations. These are the ones I wrote for modular forms. So thanks to this, then one can study the quotient HP mod gamma. And this action is nice because it's discrete, and therefore this quotient has a nice theory of analytic functions. Or in other words, it's a rigid analytic space. And like the idea is that studying this quotient should tell you some nice arithmetic information about the group gamma in a way. And the theorem that is relevant for us is what is called the Cherenkov-Grimfeld theorem. And what it says is that this quotient actually are the CP points of an algebraic curve over Q. So it's telling us that this quotient has algebraic information in a way. So there exists a curve x over Q. And for the people that like Shimura curves, this curve is actually a Shimura curve. Such that the CP points of this curve, there's a theory that gives a nice structure of rigid analytic spaces to this, and this is isomorphic to H2 mod gamma. So in a way, what this is telling us that this quotient H2 mod gamma is interesting to study. It has a nice structure, kind of interesting for number theory. So this is the object where like the geometric generalization of these theta functions will happen, but now I need to introduce a particular type of special points in this curve that are called Wigner points. So the curve x has a collection of special points called Wigner points. And these are the ones that we will really use to construct the geometric version of theta. So now I need to introduce you these Wigner points. And to do it, it's a bit more convenient to work with the following subset of the quaternion algebra, which are the elements of 3, 0. So this is now 3-dimensional. And I can put in it pairing, which is the pairing such that the associated quadratic form is the norm form in the quaternion algebra. Pairing induced by the reduced norm. So, for instance, this quadratic space of dimension 3, and it is of signature 3, 0, because my quaternion algebra was definite. So there's all the vectors of positive length. Okay, and Wigner points will be indexed by vectors in here. So for a vector v in D that has length d, and there's one condition that is called the Wigner condition that I'll mention in a moment. The square root of minus d cannot be in QP. I'm going to construct a point. So the Wigner points will be indexed by vectors of this sort. And you can see that this starts looking a bit like the theta thing we had, because the theta function was counting also vectors of length n, but with a different quadratic form. And now we're taking vectors of length. Well, I wrote d because maybe it would have been nicer if I had written n.
Sorry, can you say what this pairing is?
Yeah, so in the quaternion algebra, we have a quadratic form, which is the reduced norm form. And this pairing is the pairing such that its associated quadratic form is the norm. Yeah. And the point is that...
I'm sorry, so this discriminant of the... Is this discriminant and that discriminant are not related?
No, let me, I'll try to change all my talk and put an end. This would be the right way of doing it. I think at some point I fixed my talk and I fixed this typo, but I took some old notes. So, so if I write D, feel free to tell me. Sorry for that. Yeah, this should be N. And now the nice thing is we have an element that has trace 0 and norm N. So this element is essentially exactly like behaving like a square root of minus n inside our quaternion algebra. Because an element in the quaternion algebra satisfies an equation x squared minus trace of x plus times like t squared minus trace of the element times t plus the norm equals to 0. So this gives me an embedding of the quadratic field q squared of minus n inside B by mapping square root of minus n inside 2B. This is giving us just a way to put this quadratic space. And now we can do something to what we did with gamma to make this group act on our p-adic symmetric space. Because we can take this, view it inside the quaternion algebra, view it inside the matrices, and make it act on HP by Moebius transformations. And one can study this action, and this action actually has precisely 2 fixed points. That I'll write by zip CV and zip CV bar. So I'll go to discuss this in a moment, but I think it's better if now I define what the Wigner point is, because we're so close. Because a Wigner point is simply a point that is obtained this way. So a Wigner point in HP mod gamma is a point of the form ZCP, the class of this, or this other fixed point, ZCP bar, in this quotient, for some B as above. So for every vector v, we got this embedding of length n, we got this embedding of q square root of minus n inside b, and we took fixed points. And you can see that fixed points by Moebius transformation, it kind of makes sense that there's 2, because finding fixed points is solving this equation. So it's a quadratic equation And the discriminant of this equation happens to be exactly the square root of minus n. And so for our fixed points to be in HP, I need that this thing is not in QP, because HP was CP minus QP. So this is the type of condition that we want. Perfect. Yeah. Okay, and maybe at this point it's worth saying that for the people familiar with Shimura curves have a modular interpretation. And these points are especially in the sense of the modular interpretation. So Shimura curves in this case parameterizes certain abelian surfaces with multiplication by this order in the quaternion algebra. And Higner points are correspond to abelian surfaces that have complex multiplication, that have extra isomorphisms. So in particular, these things, one could show that they actually are defined over, are algebraic, for instance, and have very nice properties. But for the aim of this point of view, we don't really need it. We took this point of view of special points, which are points that have some large stabilizer. Okay. So now at this point, I'm ready to be able to tell you what's the geometric generalization of theta. And this, so now we go into this Gross-Kohnen-Zagier theorem. Okay. So let me take R0 to be the elements of our order, but the ones that have trace 0 intersected with B. So this is a Z1 over P lattice. Great. And now we can say what will be the geometric analog of the Rns. So the geometric analog of the Rns will be as follows. So you get, it will essentially be the sum of all Higner points that correspond to vectors of length n. That's the idea. And it seems reasonable as before we were also counting vectors of length n, but now, so we take a sum over all vectors in V mod gamma, so this is slightly different. Those that have length n, and before we were only counting the number of vectors, but now, since we have this point attached to it, we can consider the divisor, which is the sum of the two Higner points attached to it, and we take the sum of all of them, and then this naturally, since we do the sum with gamma, it will give us a well-defined, a nice object in HP mod gamma. And this is the type of thing that we'll play with. Sorry for that. Okay. So now you can see that this, in a way, it's counting vectors of length n, but we're putting, instead of just putting the counting, we put these 2 points. But based on what we saw then of our original example of a theta series, then maybe it doesn't look crazy to believe what I will write now, which is that if I make a generating series that I'll call degree of G, where here there's a constant term that is actually 1 minus the genus of the Shimura curve. And then for the rest of of terms, what we're going to put is the degree of these divisors. Oh, sorry. I don't want to call this Rn. I want to call this delta n. Sorry for that. The degree of the divisors delta n times p to the n. This is a modular form. It's a modular form. In this case, it has weight 3/2. But I mean that it doesn't look crazy because if we just take the degrees of these divisors, we're counting vectors of length n. So it's true that it's slightly different because here we have a quotient by gamma. Oh, and now I realize that for the mistake, we sum over the lattice R0. It's true that we have a Z1 over P lattice, but this sounds, I think that it sounds quite believable that this is true. And this is not very hard to prove because it's really related to a theta series as the ones we saw at the start, but for the lattices related to R0. So let me check the time.
Okay. Is G also an object or is this no notation?
Yeah, the object will come in a moment. Yeah. So for instance, like, so there will be the idea to show this would be to, let me take L a ZP lattice, a unimodular ZP lattice. And now what I could do is I could consider a theta series that I'll call theta L. And the way this theta series would look is I take a sum over vectors in my Z1 over P lattice intersected L of Q raised to the length of the vector. And my point is that this, you should believe that it's very similar to the first example that we saw where we're summing over a lattice. This was a Z1 over P lattice and this is a ZP lattice. So now this is a Z lattice. This should be in P, tensor to P. So this is believable that it's a modular form of weight 3/2. And now the point is that the degree of G can be written as combinations of theta series of this form because we're summing vectors of length n in R0. So from there, the degree of G, it's actually for maybe the experts, is a P stabilization of some combination of theta series of this form for several lattices L. So my aim on writing this is simply to write down another example of a theta series and to remember this fact that the degrees of these delta n's are just counting vectors of length.
And for P stabilization in that case, is it just going through the genus of L or the
So if you go to the genus of L, going over the genus of L, what it takes into account is this fact that you are standing over R0 mod gamma. But this P stabilization is something a bit more, because the idea is that here, when you sum over here, you can have vectors that have length d, but such that the square root of minus d is in QP. Just because this quaternion algebra is split at p and there's no condition. And so you need to do something to kill these ones. And therefore you need to work with the UP operator to make this disappear. But it's not a very serious thing. Like, without the P stabilization, this is also an interesting object and essentially has the degrees, but has a bit more information that we don't need for that. Yeah. Okay. But I think that at this point, the thing is that maybe it would be kind of too nice or too wanting too much to just call that this is a geometric generalization of the theta function that we saw at the start. Maybe it's more accurate to say that this is a geometric interpretation of these theta functions. We're just saying that these divisors, we're just interpreting theta series as degrees of divisors. But one actually has more than this, which is that one can make a modular form with the classes of these divisors. And this is what maybe deserves to be called a geometric generalization. And this is the Gross-Kohnen-Zagier theorem. Gross-Kohnen-Zagier. And in this case, it was proven by Borchert for the first time. And this is the theorem that we reproved using p-adic methods. But what this theorem says is that if I now make a generating series G, that is the one Paul was looking for, so some constant term that I will not write down now, and then for the Fourier coefficient at q to the n, we'll put the class of these divisors delta n, and we'll do this as a generating series now valid in the Picard group of HP mod gamma. So the coefficients are not numbers, but are classes in the Picard group. Tensor Q. And the claim is that this is a modular form. A modular form of weight 3/2 with values in the Picard group of HP mod gamma. So here there's a new object I have to introduce, which is what it means to be a modular form with values in a group. Like before, the modular forms had Q expansions that were numbers, and these were just functions, but now it's a bit more involved because you have a modular form that the coefficients are elements in the Picard group. But what this means is that for every functional of the Picard group to, let's say, the complex numbers, if you apply the functional to each of the coefficients, you'll then get an honest expansion, and the claim is that this is a modular form. So an example of functional would be the degree map, and then this would be the statement that this is a modular form would be this proposition over here. But the point is that there's more interesting or other very interesting functionals to apply. And this is the one that we'll focus now in a moment. Perfect. So the type of functionals that could be interesting. So we will focus on the following functional. So this Shimura curve, one interesting thing that they have is that if you look at its Jacobian, the Jacobian has elliptic curves inside as quotients of it. And this is a very useful way to understand things about elliptic curves. So let me take E, an elliptic curve, over Q, appearing in the Jacobian of X, or P0. And by this, what it means is that there's a map from the Jacobian of X to this elliptic curve. And the type of functional that we'll consider is essentially this projection. So we will study, and I'll call it phi sub E. And this will be a map that will go from the Picard group of HP mod gamma, and I want to end up in the elliptic curves. So what we're going to do is, maybe here I'll write P0. When we have something in the Picard group of HP mod gamma, I'll make it of degree 0. I'll explain in a moment how, but this is not a big issue. And now when we have something in the Picard, the big 0, I can project it into the elliptic curve. And in particular, in this case, the civic points of the elliptic curve. I'm running out of space, so this one will be long. And now, the elliptic curves that appear in the Jacobian of a Shimura curve, they have multiplicative reduction at P. And in practice, what this means is that we can understand them as Cp star mod Q to the Z. So usually we see complex uniformizations of elliptic curves as C mod the lattice lambda. But for the CP points for certain primes P, you can also write them like this. And whenever an elliptic curve appears as a quotient of a Shimura curve, for the primes for which we have p-adic uniformization, you also have that. And now finally we can apply a logarithm, a p-adic logarithm, to map these to CP. Sorry, this happened to be longer than what I expected. But the point is that we have a functional from our Picard group to numbers. Now we can apply the functional to this generating series and get some honest Q expansion made out of numbers. And the point is that this thing is a modular form. So we will study the modularity. What do this? We'll study it. Of phi. Okay. Okay. So maybe before saying some words about how to prove this modularity, I'll mention just one application of this. So the idea is that indeed, like once you know that that these things package into the coefficient of a modular form, since modular forms satisfy a lot of nice symmetries, the point is that you can then deduce things about these numbers. Sorry, now I messed this up. The modularity of P of G. Like in the same way that for the theta series we deduce a lot of things about the Rn's, thanks to this being the modular form.
This is valued in CP.
Yeah. Yeah, so this is a bit, but the point is that since one way of seeing it, I think, is that since this Picard group, maybe it's related to the Picard group of the Jacobian of a Shimura curve, that then this has a model over Q. To study the modularity, you can either study morphisms to the complex numbers or morphism to CP, for instance. Because there will be something like it will be just some sort of change of scalars, like tensoring by something. And for instance, like so this being a modular form, what it will mean is that it will just be an honest modular form with coefficients in Q or in some algebraic extensions, tensor with a number in CP. That's what being a modular form will mean. And this essentially applies the result with some annoying like algebra. Yeah.
If there is an isomorphism of CP and C, so we'll get a modular form over C.
I think that's it, isn't it? I mean, CP and C should be isomorphic just as abstract fields.
Yeah.
And as long as the coefficients are in some number field, the only thing that might change if you change the isomorphism is some Weber action, and Weber group acts on the spaces of modular forms, so it's fine.
Yeah, I would believe that something like this could work also. Yeah.
Okay.
Like the idea is that in the end the spaces of modular forms are always finite dimensional and with coefficients in the algebraic numbers. So there's always putting coefficients in here in CP or in C is only one annoying constant you put in front, but the modularity is still the same. Yeah. And like for instance, one nice thing is that you can do once you know the modularity of this, and this is how you can understand things about finger forms. So for instance, the Gross-Kohnen-Zagier theorem for this generating series, phi G, what it tells you is that the rank of the span of these points, phi delta n, where we run over all n. So phi of delta n are points in the elliptic curve. And what this tells you is that the span of all of them It's actually smaller equal than 1. That's something that can be deduced out of it. And this is something like, so Gross-Kohnen-Zagier studied a lot these signal points delta n, because they give a way to produce points in the elliptic curve that are actually rational. And these points are always expected to be non-trivial when the elliptic curve has rank 1. But on the other hand, you have so many points delta n, 1 for every n. So at some point, they got a bit afraid, saying, "Oh, damn it, we have so many points, but they should span only something of rank 1." So then, for instance, this Gross-Kohnen-Zagier theorem implies that they span exactly what they should be spanning. So that was a good sanity check. Nowadays, there's other techniques to study this, but that's something that was done. Okay. And like one other advantage of this formulation that is purely p-adic is that it allows you to prove modularity statements for things that you don't know that they are algebraic. And so then you can deduce, for instance, that they span, that the group of their span, sorry, that the group they span has relatively small rank, and therefore, for instance, if one is algebraic, then the others, you could deduce that they are algebraic or things of this sort. Okay. So now the last thing I will do is I'll say one of the ingredients that appears in the proof. So I don't have a lot of time, but so I'll just be very brief. But this ingredient, it's called the p-adic families of theta lifts. An outline of proof. Okay. So now I will explain, I will construct what is one of these p-adic families of theta lifts, and then I'll write a bit how we deduce the modularity of this Gross-Kohnen-Zagier generating series using these p-adic families of theta lifts. Okay. So for this, let me take L, again, unimodular ZP lattice in the tensor P. And now I'm going to take W, a vector in L, such that it has length 0. So then, we're going to make some theta series. So consider, and I'm going to call them theta K, W. So when we make some theta series, we want to sum over Z lattice. So the type of Z lattices that I will sum is R0. This was a Z1 over P lattice intersected with L. And now, usually when we make theta series, what you would do is you would put Q raised to the length of the vector. If you do this, what this gives you is a modular form that has weight the dimension of the quadratic space divided by 2, 3/2. And now what we're going to do is we're going to make a collection of modular forms, but where the weight will change. And the way to do this is to add here the pairing of B with a vector of length 0 to the K. The idea is that, as I said, to prove modularity of this one, use Poisson summation formula, and that the Fourier transform of the exponential behaves nicely. So that if you put the Fourier transform of the exponential times this is a function that it's called harmonic. So it also has some nice differential equation. And therefore, this also transforms nicely under Fourier transform. So this actually becomes a modular form of weight 3½ plus k. So now we have a collection of a lot of modular forms. And finally now, I want to make out of this what is called the p-adic family. And for this, what I'm going to do is I'm going to add and sum only, put here a characteristic function of the vectors such that they pair to a p-adic unit with W. This is the characteristic function of the elements that pair to a p-adic unit with these fixed vectors of length 0 that we took. The nice thing if you do this is that now this number is always a p-adic unit, and now it will satisfy. What happens is that with these numbers, if we start changing k, they will satisfy a lot of nice congruences. And this is by Fermat's little theorem, in a way. So, if k is congruent to k prime modulo p to the r times p minus 1, then this number will be congruent to this number modulo p to the r plus 1. This is just like kind of Euler's theorem. And so what this means in a way is that this family of modular forms that we had varying with k, the Fourier coefficients of this family vary continuously with the variable k. And one can even refine this and not only get a continuous variation, but an analytic variation. So we don't have only a modular form, but we have an analytic family, a family of modular forms such that the Fourier coefficients vary analytically. And the nice thing is that one hope that with this with families of modular forms, we can encode a bit of more refined information than not just what modular forms could encode. And this is a bit what we did. So this, for instance, is something that has an Archimedean analog, where the Fourier coefficients vary analytically with respect to the Archimedean metric, and here we have that the Fourier coefficients vary analytically with respect to the p-adic metric. And I'm almost done. So what we do is we construct a p-adic family of modular forms like this one, but taking some linear combinations of elements in here. So there exists a p-adic family of theta series or modular forms of weight k plus 3½ that I'm going to call theta of k, and this family satisfies two properties. The first property is that the specialization at k equals to 0, so it's the specialization in weight 3½ is 0. So then at this point, maybe this doesn't look too interesting. Also because in weight 3½ is the time where we were, that was calculating degrees. But what we actually do is that sometimes in number theory, when something vanishes, you take its derivative from n at k equals to 0 of this family. And we apply something called the p-ordinary projection. So here what we're doing is we're taking a derivative in the coefficients. And what we show is that this is actually equal to the generating series of Gross-Kohnen-Zagier after applying t. And the nice thing is that the theory of families of modular forms allows you to prove that this left-hand side is a modular form, because derivatives of families of modular forms have some nice theory. So left-hand side is a modular form. And therefore, we deduce that CG is a modular form. So like the summary in a way is that to study the degrees of G, you can use a regular theta series, and to go into actually Figner points or more refined arithmetic information, you do some small modification to the theta series by putting it into a family, and you study the derivatives. And I'll finish here. Thank you very much for your attention.